So the first speaker, Leto, is not. He's going to talk about unifying integrable PFTs in ABS noble theorems for higher tensor.
Thank you very much. Should I turn this on?
You are loud enough.
Hello. Okay, I can be very loud. Yeah, so thank you very much. And yeah, first a huge thanks to the organizers for putting together this lovely conference. And yeah, thank you very much for the chance to speak. So I'm going to tell you about our recent work with my excellent collaborators, Antonio Antunes and Marco Mineri. And so we were interested in the question of whether there are integrable quantum field theories in curved spacetimes, like ADS2. So this naturally led us to think about higher spin conserved charges in ADS2. And then, somewhat surprisingly, we found that these are very constrained. So actually, in the end, we were able to prove no-go theorems, which I'm going to tell you about. So before I come to ADS2, let me make some remarks about flat space. So in flat space, in 2 dimensions, something marvelous happens. There exist these exactly solvable quantum field theories. Not just trivial free theory, but genuine, interacting, non-trivial, solvable 2D quantum field theories, like Sine-Gordon. It's governed by a beautiful integrable S matrix, and it has factorization, and many aspects of the theory can be exactly solved using integrability. And so you may ask, do there exist similar structures in anti-de Sitter space? So can you write down some exactly solvable quantum field theories in ADS2? But this is a kind of, let's say, ill-posed question, because you don't really know how to define integrability, even in flat space. The working definition in flat space would be there's a factorized S matrix. But you don't really know how to generalize that to ADS2. What would be analogous property? So instead, we're focusing on higher spin conserved charges as a sort of proxy for integrability, based on the observation that, like, all examples we can think of in flat space have these conserved higher spin charges. So we're asking this well-defined question: do there exist quantum field theories on ADS2 spacetime with local higher spin conserved charges? And the answer is, at least in the perturbative vicinity of free fields, no. So there are no weakly coupled such theories. And you can think that this work is somewhat sort of morally related to this quite well-known work of Malostin and Zhivayev, where they asked a similar question about 3D CFTs. And what they showed is that 3D CFTs with higher spin conserved charges must be free. But any questions about these statements before I move on? This is really the punchline. Yes?
When you say they must be free, do you mean they must have trivial scattering?
In the Malostin and Zhivayev case, in 3D CFTs. So in this well-known work, I mean, it's about CFTs, right? So it's not really about scattering. Basically, to show that the correlation functions of the theory need to be those of a free theory. So they show that there are no non-trivial, like, interacting 3D CFTs with higher spin conserved charges.
So would you say for the Sitter too, you would have the same statement?
I actually expect, I mean, we don't really know that well how to understand even quantum field theory in de Sitter,
Yeah.
but I kind of would expect similar statements, because as you'll see, what's going to be important in this game is that the isometry group of ADS2 is simple, unlike flat space. And that's also true in de Sitter. So naively, I would say it's probably not so different.
So by higher spin, this is in the context of software?
No.
Oh.
I'll say what I mean by higher spin. Yes.
Yeah, but when you talk about 3D CFT, so you're talking about higher dimensions and food. So is that somehow analog to Coleman-Mandula theorem?
Yeah, I think that is a very close analog to Coleman-Mandula, yeah. So again, my result is about ADS2, but I was just mentioning this work.
Yeah. But ADS2 is still 1+1, right?
So I'm focusing on 1+1 ADS2.
Yeah.
I was just mentioning this kind of well-known work in 3D CFTs.
Yeah.
But our work is about 1+1.
Okay.
Yeah. Okay. So I'll begin with some motivation, then I'll introduce higher spin charges, and then I'll talk about free fields and deformations of them, and then I'll talk about another class of theories, which are CFTs in ADS and deformations of them. So I don't need to tell you that integrability is a super interesting and powerful tool that exists in some special quantum field theories in 2 dimensions. So there exist these sort of remarkable, exactly solvable interacting quantum field theories. I wrote a list of them here, including our favorite integrable deformations. But these theories are characterized by some higher conservation laws, which can be shown to imply factorized scattering. So you have this sort of remarkable factorization of the S matrix into 2 to 2 S matrices. So it is a natural question. Is there some analog of this structure in curved space? Right? Like what would be the analog of this Yang-Baxter relations, etc. in a non-trivial space-time? And I'm particularly interested in ADS for the following reasons. So quantum field theories in ADS enjoy a kind of rigid version of holography. So even though the graviton is switched off in the bulk, so the space-time is fixed to a rigid ADS background, so that means that the boundary CFT doesn't have a stress tensor. Still, the on-shell observables of the theory are governed by conformal invariance. So I get these sort of conformal correlators on the boundary. You might not like this kind of CFT that doesn't have a stress tensor, but in the end, it has all the properties you need. It has a discrete spectrum, satisfies conformal invariance, and it has a convergent OPE. And moreover, ADS acts as an IR regulator. So if you have some problem with, if you have some gapless theory and you have some IR problems, you can just couple it to ADS and in principle solve these problems. And one thing which is nice is that these CFT correlators have a well understood flat space limit. So when the ADS radius becomes large, they literally map onto S matrix elements in flat space. But there's another reason which I want to kind of sell to you from the conformal bootstrap, why we wondered about these QFTs, these integrable QFTs in ADS2. So QFTs in ADS2 can be described as some one-dimensional CFTs on their boundary. And CFTs in general are amenable to this amazing non-perturbative method called the conformal bootstrap.
What's the one-dimensional CFT?
Take your favorite QFT in ADS. The correlation functions on the boundary are an example.
Okay, but how do I define it if I don't know anything about ADS?
Well, I mean, there are examples where there's a first principle definition, but in principle, you also don't need one. I mean, you can just think that this is basically an S matrix for a theory in ADS. But there are examples. For example, long-range Ising model, which I'll mention later. It's basically, well, this theory has a definition in its own right, and it's an example of this structure. Yeah. So what's the conformal bootstrap doing? So it's basically just using basic consistency relations, unitarity and locality, and conformal symmetry to eliminate large regions of parameter space. And surprisingly, this works very well. So here I'm showing this famous plot for 3D Ising model. And what I want to emphasize here is that in general, you get some little island in the bootstrap, and the target theory is somewhere in the middle of the island. But what the bootstrap's really doing, it's not finding that theory alone. It's basically just finding a bunch of theories nearby to it that saturate unitarity bounds. And the reason, so the numerics basically seem to stop converging when they hit some solutions, which are called extremal solutions. So the bootstrap is basically carving out some family of special extremal solutions nearby to, say, Ising, which saturate unitarity. And this means the unitarity bounds can't be improved anymore. So basically, the bootstrap is finding some kind of idealized CFT solutions nearby to the one you're looking for. And these extremal solutions have some special properties. So their spectrum, unlike Ising, which is chaotic and dense spectrum, these extremal solutions have a sparse spectrum. They look more like generalized free fields.
Sorry, Ising as a chaotic spectrum?
It's believed to, yes. 3D Ising, yeah. And these things, as I mentioned, they saturate unitarity bounds. So these are some very special solutions. In general, in higher dimensions, like in 3D, we say that these extremal solutions are not physical. If you just increase the number of correlation functions that you study, the island will shrink. So these things just go away. But in 1D CFT, you might fantasize that some of these things, because these kind of feel like integrable type properties, you might fantasize that some of these things could have an integrable description as a QFT in ADS2 in 1D. Because they have this, because you're in this special case where the bulk ADS theory would be 2-dimensional. So we had some hints from the conformal bootstrap that you might expect it might be kind of useful for the bootstrap, and it kind of gives a hint that you might expect some integrable theories on ADS2. So aside from all these motivations, another point is that we actually have a good candidate theory. So the supersymmetric Wilson line in n equals 4 is a 1D defect CFT, and its planar spectrum is solvable thanks to the integrability of the 4D bulk theory. So that 1D CFT is dual to an effective quantum field theory in ADS2, which is basically describing fluctuations around the minimal area world sheet ending on the Wilson line. And its action is given by this Nambu-Goto type action. So you should expect that this theory is in some sense integrable, right? The CFT spectrum on the boundary of this ADS2 theory can be solved using integrability. But in what sense can you understand this as an integrable theory? What's the analog of like factorized scattering or no particle production for this quantum field theory in ADS2? It's very unclear.
I'm still, I should
Sure.
have a last confusion. Why ADS2? I mean,
This is ADS2 metric.
sure, but don't you need the, I mean, quantum fluctuation will probably have to do with the whole of ADS5, no? After all, it comes from 4D.
In the end, the Wilson line specifies some boundary conditions, and after gauge fixing, you can write the string sigma model as this QFT on ADS2. So we have a good candidate theory that seems like it should probably be integrable. So let me now turn to higher spin charges. So as I mentioned, integrability is related to the presence of higher conservation laws. And one class of these are associated with the flat Lax connection and its monodromy and the resulting non-local charges. And instead here I'm going to focus on local higher spin charges, which is another class of these higher conservation laws. And these are pretty much ubiquitous in integrable quantum field theories that we know in flat space. So these higher spin charges alone are sufficient to imply factorized scattering. So is there some analog of this statement in ADS? Right? If I assume some higher spin conserved charges in ADS, can I derive some statement which is analogous to factorized scattering? So what are higher spin charges? So here I'm defining a higher spin charge as the charge obtained by integrating a higher spin conserved current. So a higher spin conserved current is just a conserved current which is symmetric and has some higher rank. So like an example we all know is the stress tensor, which has rank 2. And you need to contract this conserved current with a killing tensor in order to get a conserved charge. So the resulting charge is conserved in the sense that it's topological. So I can move the charge defined on a curve, I can just move it around in the ADS2 space. And if I go through an operator insertion, then I'll pick up the action of the charge on this operator. So an example of a theory which has a whole algebra of these higher spin charges is just a free theory, as you might expect. So consider a free field in ADS2. Could be a scalar or a fermion. Here's the scalar. It has a whole algebra of conserved higher spin currents and the resulting charges. Here I've written down the spin 4 conserved current. And so we get currents with every even spin. And so the resulting charges form what's called the higher spin algebra, which depends on the mass of the field. And this tells you certain things about the theory. So then you can conclude from this that all operators in the dual CFT need to transform in representations of this higher spin algebra. So in this case, so the dual theory on the boundary of this free field in ADS2 is what's called a generalized free field, 1D CFT. And this GFF theory, you can learn things about it from this higher spin symmetry algebra. So you can use this higher spin algebra to conclude, for example, that the GFF theory has integer gaps in its spectrum. So the spectrum of primaries is like this.
Sorry,
Yes.
Generators for these charges, as you said, are traceless symmetric tensors, right? Or
No, in general, not necessarily. Well, yeah, you can use the basis of traceless symmetry. Yeah.
right, but then those guys are exactly the ones used in soft theorems.
Sure. Yeah.
But they, well, I guess you're not proving the stop here, but typically I see them in asymptotically flat spacetimes, right? But
I mean, in principle, you can have these charges in flat space or in curved space.
yeah.
So
but
these statements, for example, this current, you can get a high spin current in flat space by just replacing
Yeah.
covariant derivatives with derivatives.
Very nice. May I ask, so are there also other currents which have mixed symmetries?
What do you mean by mixed symmetry? Sorry.
So not totally symmetric. I mean, you could write down other Young tableaus, right?
No, I think I only have symmetric tensors.
Okay, and they form an algebra, which is this higher spin algebra.
Yes. So I would have the same structure in flat space, right? As we just said, replacing covariant derivatives with usual derivatives. So let's try and understand. This is for a free theory. Now let's look at like a simple example of an integrable model in flat space that we know, and try and see how it deforms this structure. So let's go back to Sine-Gordon model. So in flat space, I would have a fully conserved higher spin current for every even spin. Now when I turn on Sine-Gordon potential, I actually break this structure to only a subset of these current. So I just get conservation parallel to the null direction, z and z bar. So this fully conserved current is not fully conserved anymore once I turn on the Sine-Gordon potential. It's only conserved parallel to certain directions. So in our language, we could say that the projection of the current along certain Killing tensors is conserved, but this higher rank current is not fully conserved. So Killing tensors parallel to z and d bar. So this means you only get a subset of the charges in this simplest integrable model that we know, Sine-Gordon. So now a key observation in the story is that that's simply not possible in ADS. So in ADS instead, as we said, it's basically because the isometry group of ADS, SL2R, is simple, whereas the Poincare isometry group of flat space is not simple. So it has these special null directions. In ADS, that's just not possible. So in ADS, any partial conservation equation implies full conservation. So it's simply not possible to have the structure that we had in Sine-Gordon model in flat space in ADS. And it's really because of this simplicity of the isometry group of ADS. So yeah, just to kind of highlight, right, this is a Killing tensor, which when you act on it, when you transform it with isometries of flat space, it would just get mapped back to a multiple of itself. But there is no such Killing tensor in ADS. And so we have kind of detailed argument, maybe I won't go through the details, but the argument is just you start with a partial conservation equation and you act with isometries and you observe that you can deduce full conservation. You can basically turn this Killing tensor into any symmetric tensor. So you conclude the current is fully conserved. So we already see that it's doomed, right? These non-trivial quantum field theories in ADS with higher spin charges, it seems very difficult because the minimal possibility is to maintain the whole higher spin algebra. And you expect that this higher spin algebra is sort of characterizing free theories. It's sort of associated with free theories. So the minimal possibility in ADS is to preserve the whole higher spin algebra. So now let me turn to the main result. So starting from a free field, a massive scalar or fermion, Majorana fermion, in ADS2, consider continuously deforming by any interaction in ADS, so respecting ADS isometries. And the result is that it's impossible to preserve any higher spin charges. So I should give a couple of caveats. We're talking here about continuous deformations. So we assume that, for example, you're not coupling in any extra states when you deform the free field. And we assume that like observables like dimensions and OP coefficients depend continuously on the deformation. So these are assumptions. They're kind of reasonable assumptions. Like in examples, we know that if you just write down some Sine-Gordon action in ADS, you'll find that these are satisfied. So the way to argue this statement is just, first, as I already told you, the minimal set of charges you could possibly have is the whole algebra. So it's very constraining. And it's sort of easy to argue like this because you start from a free theory and then deform. And then we also know how the charges act on the fields. So I have some operator which was this generalized free field. That's the boundary value of the field in the bulk. And I knew how these charges act on it in the free theory, but just by like some derivative to make the sort of correct weight. And the point is that in the free theory, you simply cannot, there are no operators you could write down. No additional operators you could write down on the right-hand side. No primaries with the right scaling dimensions, not even close. And this means when you deform continuously in some neighborhood, there are still no operators you could write down, right? The scaling dimensions can't jump. So there's simply no corrections you could possibly write down to this equation. So now you know how the charges act on the operators. You can just write down ordered entities from the presence of these charges. And you see that we have, for each correlation function, we have ordered entities for all even spins. So it's a very overdetermined system. So naturally, as you would expect, the only solutions are generalized free fields. There are two solutions. Depending on the statistics of this field phi, you can either have generalized free boson or generalized free fermion, which corresponds to free scalar in ADS2 or a free fermion in ADS2. Now let me just quickly state our second result. So this is about CFTs in ADS, which are sort of trivially related by conformal transformation to boundary conformal field theories in the upper half plane. And we're talking here about Virasoro CFTs, and we're assuming a Cardi condition at the boundary, so there's a diagonal Virasoro that's preserved. The universal enveloping algebra of this Virasoro contains higher spin charges, as is explained by Zamolodchikov. Here's an example, spin 4 current and a spin 3 charge. There's a full family of spin 3 charges by taking different killing tensors. And some of these are related to this KDV hierarchy of BLZ. So the no-go theorem here is if you start with this structure, a CFT in ADS, and you deform by any single relevant or irrelevant Virasoro primary, and so you have an RG flow in ADS, it's impossible to preserve any spin 3 charges. So here we're just focusing on spin 3. It would be interesting to think about higher spins in the future. And so this rules out the direct analog in ADS of these phi1 free flows between minimal models, which are probably very familiar to many of you. So these guys would normally preserve some spin 3 charges. So a sketch of like possible quantum field theories in ADS with higher spin charges is this. There are Virasoro CFTs in ADS, and there are free fields. And at least in the perturbative vicinity of these blue lines, there's nothing else. There could be other things far away. Before I wrap up, let me just tell you something not related to integrability. So we also studied long-range CFTs, and these are interesting. They actually appear in experiments. So these are interesting theories, and these are basically, you can think of them as a free field in ADS2 plus some boundary localized interaction. In general, there's an RG flow, and the couplings in this, so you could put a general potential here, and they'll flow to some infrared fixed point. This is called a long-range CFT. This example here with phi4 is long-range Ising. And our no-go theorem here is that long-range CFTs cannot preserve any higher spin charges at non-trivial interacting fixed points. The power we get here, we don't need to assume kind of perturbatively close to something, basically because the theory is always free in the bulk. So you always have a free wave equation in the bulk. The interaction is always localized to the boundary. So that gives you a lot of power. And you can actually conclude from this breaking of higher spin symmetry by the boundary that there exists some protected integer dimension operators, which are like the analog of displacement operator for the breaking of translations. So to wrap up, free fields and CFTs in ADS have conserved higher spin charges, but they resist higher spin preserving deformations in ADS. And this is really different from flat space. And this really happens because it seems to be all or nothing in ADS, really because the isometry group of ADS is simple. So you can't just preserve these special null directions. So if integrable field theories exist in ADS2, then conservatively I would say they're disfavored to have higher spin conserved charges. At least analogs of Sine-Gordon and minimal model RG flows shouldn't have higher spin conserved charges. We also showed that long-range models can't have higher spin charges. In future, it would be interesting to close certain loopholes. So there are some exceptional cases, like special values of the mass of the free field, or multiple fields with tuned masses relative to each other, which we didn't address. In the CFT case, we only addressed spin 3 charges. It would be interesting to address higher spin charges as well. Another thing which would be very interesting to study is the weak breaking of higher spin symmetry at large ADS radius. If you have some quantum field theory in ADS, which becomes Sine-Gordon in the flat space limit, you know that it inherits, it gets higher spin charges when the radius goes to infinity. And for large radius, this would probably be very constraining because you know that the higher spin symmetry is only weakly broken. So finally, if you're kind of devoted to the idea, which I think is a reasonable idea, of integral theories in ADS2, then probably you shouldn't think about these local structures, these higher spin charges. Perhaps in ADS2, you really need to focus instead on non-local structures. Maybe when you deform to ADS2, you only get these lax, monodromy, non-local charges, Yangian quantum groups. So that's an interesting direction for the future. Thank you.
Thank you, Matt. Thank you.
Go back to this long range.
Yes.
So this is DFT1, right?
Yes.
And does it mean that it has some dinosaur, or is it like not really realized? No.
SL2R.
So CFT1 doesn't mean dinosaur, it only means
No.
CFT1.
No.
Okay.
I mean, this class I showed you, CFTs and ADS. Here we have Virasoro. We had two copies of Virasoro in 2D, and we assumed Cardi condition. Well, here we have Virasoro at the CFT, but then we're deforming by an RG flow.
No,
So once you deform,
was
it's only CFT1 SL2R conformal group. Yeah.
The string Lagrangian you showed, is that should Virasoro be imposed on top of that, or was that
Which Lagrangian?
the worldsheet string Lagrangian?
The square root.
You're talking about
Nambu
constraints.
Goto.
Yeah.
Oh, sorry, that was Nambu Goto.
Yeah. So here it's Nambu Goto, yeah.
So if you expand this up, so you need to gauge fix this somehow.
So here gauge fixing has already been done. It's kind of like a kind of uniform Lycombe gauge type thing.
And this thing has full SL2R invariance or not?
Yes. I mean, yeah, this is the only tensor that appears here is the metric of ADS2.
I'm just thinking an analogy with like the MN Lycombe gauge, where you have like the leading term is a free theory which has Poincare invariance, but then the corrections break Lorentz invariance. And I'm just wondering,
Yeah,
you can imagine like a free theory that's on ADS2, but then perturbations that break SL2R that somehow you can have that preserve the higher spin charges.
Yeah, I mean,
But I would need to look.
I sort of get the analogy you're making. Curiously, it looks. I mean, this theory looks like it just satisfies ADS2 isometries.
Yeah, sure.
Maybe I'm missing something in the fermions, which I didn't write down, but I don't think so.
Okay.
Yeah, it's a good question. Yes.
No. Sorry. So the index mu is the So what I wanted to ask is, shouldn't the derivatives be covariant derivatives there, or is it? Are covariant
Well, because these are
derivatives
scalars.
So they are
This is
scalar
the-
fields, and so that's
Yeah,
why the
yeah.
covariant derivatives are the partial derivatives. Okay.
Yeah.
Okay, let's thank Nat.
Thank you very much.